In this video, I'm going to give a high-level overview of algorithms and also talk about why we study those. So let's start with the question of what is an algorithm? So an algorithm really is just a set of directions for performing a task. So let's give an example. Calculate your homework average. I think that if asked to do this, most people follow this algorithm. First, they're going to sum the n homework grades. So if n was 10, that means you have 10 grades to find the average of. And then divide the sum by n, right? That's probably what you do. So that would look like this. Average is equal to grade 1 plus grade 2 plus ... plus grade n. You produce that first, the sum, and then we divide by n, which is the quantity of grades. But there's an alternative to that. We could also do it this way. We could do grade 1 divided by n plus grade 2 divided by n plus ... plus grade n divided by n. These are mathematically equivalent, right? So the second one would have this set of directions. Divide each of the n grades, that's two words, sorry, by n, and then produce the sum of the n quotients. Each of these is a quotient, right? So this is an example of an algorithm. Actually, these are two different algorithms for performing the same task. Why do we care? You know, what is the purpose for studying algorithms? If I had to describe the reason why we study algorithms in one word, it would be about performance. Okay? So as the end user, what you typically care about is how much time it takes to do something. But in reality, the way we're going to look at this is in terms of computational effort. That is, how many steps does your computer have to perform to do something? And of course, the way you experience it is through time. Now, an alternative that we could look at in terms of performance would be amount of memory used. I'm not really going to get into that, but that is another thing that people have to consider depending on the algorithm and the underlying task. Okay? Now, in many cases, you won't know the true amount of computational effort involved, but what you may realize is that, method B takes about, twice as many steps as method A. And therefore, if you realize that, you'll realize that method B probably takes much longer than method A. So there's the basic idea behind what an algorithm is and why we study it. So let's go back and revisit this example to see more of what I mean. So let's say we have 4 grades. So grades are 87, 95, 92, 90. So we have here n is equal to 4. So by method 1, the one most people would use, I would assume, we would say sum is equal to 87 plus 95 plus 92 plus 90, and then the average is equal to, this right here happens to be 364. I've already done these calculations. 364 divided by 4 is 91. Okay. Method 2 is that quotient 1 is 87 divided by 4. Quotient 2 is equal to 95 divided by 4. Quotient 3 is equal to 92 divided by 4. And quotient 4 is 90 divided by 4. And now we have that the average is equal to Q1 plus Q2 plus Q3 plus Q4. Okay? And this, of course, then also should be equal to 91. Now, if we're trying to figure out what the computational effort is, if we look over here, we can first account additions. So I added two numbers together, that's one addition. Add 92 to that sum, that's two additions. Add 90 to that, get three additions. But in terms of n, that's n minus 1, right? Because we realize if I had actually 1,000 grades, I would have more additions here. It would be, in that case, 999. And then I perform one division at the end. And that's true no matter how many grades are to be summed. Over here, we start with divisions in terms of what I can see. And what's that equal to? 1, 2, 3, 4, which is just our n. So if I had 1,000 grades, I'd have to perform 1,000 divisions. And then in additions, like before, that was 3, which was n minus 1. So these aren't hugely different here. We have 4 operations versus 7 operations. But keep in mind that if I had 1,000 grades, I would have 999 additions plus 1 division for 1,000 steps here, or operations. But over here, I would have 1,000 divisions before I perform the 999 additions. It's hugely different. And that's not even factoring in that I would argue that in general, if I'm performing division by hand, division is much more difficult than addition. So this is even worse by that measure. But even if they would take the same amount of effort to perform one addition as to perform one division, this is clearly much less effort than this, especially as n gets bigger. Okay? And so this demonstrates something that is true of algorithms in general. It's not an absolute, but for many algorithms, the computational effort is a function of n. That is the number of things, because they don't have to be numbers, they could be names or whatever, the number of things to be processed. Okay? So for a particular algorithm, the computational effort is a function of n. We saw that here. Once again, as n gets bigger, the amount of additions that we perform increases. Over here, as n gets bigger, the number of divisions increases as well as the number of additions. Okay? Let's look at another example that will help make this a little more clear, I think. So sorting is a common problem in computer science. We sort names, we sort numbers, whatever. So let's give you the details. In 2010, I wrote a Python program to sort 100,000 random integers. Okay, and I ran this on a laptop that I think was from 2010. That'll be relevant here in a moment. Okay? And I sorted these integers two different ways using an algorithm called quicksort and an algorithm called bubble sort. Okay? When I did that, quicksort took less than 1 second to sort the 100,000 random integers. Bubble sort took approximately 43 minutes. Once again, less than a second versus about 43 minutes. That's huge, right? Because there's a lot of seconds in 43 minutes. So that leads to the question, could I know in advance that quicksort would probably be much faster, not just faster, but a lot faster than bubble sort? And the answer is yes. Okay? So how do I know that? Right. So there are a number of factors. There are a number of factors that affect performance, but some factors are, one, the hardware used. Okay? By hardware, we mean things like the clock rate. You may have a 4 gigahertz processor. The architecture. So you may have a chip, a CPU that's made by AMD or Intel, but they have different families of those, right? I'm old enough to remember when we had Pentiums. That tells you how old I am. So that's pretty old. But that was a family, and that was a family of processors, and that's a particular type of architecture. And what that ultimately means is different architectures can have different ways that they carry out operations. Okay? Another thing that would be included as part of hardware would be how much memory do you have, as well as the speed of that memory. So there's some examples. So in my case, I used a computer from 2010, okay, but I used the same computer for both algorithms. So it wasn't that I was using a slow computer over here versus a faster computer over here. I used the same computer in both cases. But you would assume a 2022 computer, this is the year I'm making this video, assume a 2020 computer would be faster for this particular task. Okay? Another factor that can affect performance is the specific problem instance. What that means is, what data are you processing? We already said that I was using 100,000 random integers. But because I know that quicksort and bubble sort are both affected by the order of the values that you need to sort, I made a copy of this so that each was working on the same data. Because for bubble sort, for example, its best case scenario would be the numbers are already in order. So like that, 1, 2, 3, 4, depending on how it's implemented, 1, 2, 3, 4 doesn't take much time versus 4, 3, 2, 1. This assumes I want to go from smallest to largest. So this would be my best case scenario. This is the worst case scenario for bubble sort. Okay, this would take more effort versus this. So I want to compare the same data in both cases, so I made copies. And then the third thing that's a factor here, out of the ones I'm naming, that you could probably come up with others, but this would be the particular algorithm. That is specific steps. If we go back to this example right here, I would argue that this version is better than this version, not only because this has more overall arithmetic steps, right? But some of those steps, a lot of those steps actually, more than half are divisions, which I would argue that in general take more effort than additions. So if these were all additions and these were all additions, this would be worse. But because half of these are divisions, I think that makes it even worse than this. So this is arguably better than the other one. Okay? So in an algorithms course, you typically look at 2 and 3. Okay? So what can we do about the algorithm part? Well, it turns out that what we can do, and this is what you learn in an algorithms course, is you learn to calculate the computational complexity. Of a particular algorithm. That is, you're looking at coming up with a function of n for it that lets you try to compare in advance how many steps would they take. So let's look at some of the values you would have for each of these. This isn't the actual analysis. This is just to give you a high-level overview. But one of the things you can do, you don't necessarily know in advance how long it's going to take, or even the exact number of steps without a tremendous amount of work. But what you can do is you can put a bounds on the number of steps for different scenarios. So bounds could be lower or upper. But typically people look at the upper bounds, that is, it shouldn't get past this. And for that, we'll end up looking at what's called big O notation. You pronounce it big O, but it will be written as something like this. O of n squared would be an example. Okay? So for quicksort, for the best case scenario, we have it has a big O of n log base 2 of n. Its worst case scenario is big O of n squared, and average case scenario is big O of n log base 2 of n. So what does that mean? Well, like in the case of worse, it's saying if you have n numbers to process, it would take approximately n squared number of comparisons of those numbers. Because if you're sorting, you have to ask the question, is this number bigger than this number? And if so, reverse the order. Okay? For bubble sort, and once again, in both cases, there's different ways to actually implement the algorithm, and they can affect performance in and of themselves. So best case has a big O of n, so n is less than n log n. So this would be better if, in the absolute best case. Worst case here is big O of n squared, but then average case, all the other possibilities, is big O of n squared. So I already said that, like in the case of bubble sort, best case would be something like this: 1, 2, 3, 4. That is, it's already in the order you want. Worst case would be completely the reverse. And average is based upon trying to sort of average out all the other possibilities. Because think about it, you could have something like this: 1, 4, 3, 2, and 2, 3, 4, 1, and lots of other possibilities. These are going to occur in many cases much more often than these. It would depend on your problem, but you don't necessarily know the order. But like for what I did, I just generated the numbers at random. And so let's see how these sort of help me know in advance that quicksort probably was bubble sort. So why do I say probably? Well, even though I generated the 100,000 random integers, or generated the 100,000 integers randomly, there was always some possibility I was going to get something that was already in order, which could have made bubble sort better. But it was highly unlikely. So if we go with average in both cases, n log n versus this, well, n in this case is 100,000. I mean, in both cases, 100,000. And so n log n was equal to 100,000 times log base 2 of 100,000, which is approximately equal to 1.7 million. So that means on average, quicksort had to perform approximately 1.7 million comparisons of numbers. Okay, once again, as I said before, it's actually dependent upon the particular order of the values, but we're going this as a generalization. But for bubble sort, because we have n squared comparisons on average, that's 100,000 squared. 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's in the U.S. There's thousands, millions, billions, about 10 billion comparisons versus 1.7 million. Okay, so to help put it in perspective, it's that. That's the reason why we had less than a second versus about 43 minutes. Okay, that's huge. So in future videos, I'll talk about give more of an actual formal definition of what big O is, as well as some of the other measures that you use for putting on bounds. And I also will make some videos in which I actually show how to calculate the big O value for different algorithms. Because while you can look these up online, in an algorithms course, you're supposed to be learning how to actually produce these values yourself, at least for the simple ones. There's some that would be very difficult. Like, for example, what is average? Best case and worst case are easier to understand than what would be considered the average case in general. But those will be something I will discuss in future videos.